All right, so welcome to Finite Element Methods, first class, Math 574 here at the University of Tennessee. So the way I'm going to do this is I usually kill myself writing out or LaTeXing my handwritten notes and turning them into beautiful slides. And this time I decided to give myself a little bit of a break and handwrite my notes because it goes a lot faster. I'm going to be following the set of notes that I posted on Canvas, but uh, not so carefully that you might that maybe you should expect some changes here or there. But you can have a look at those notes that are posted on Canvas from previous years. I think there are 29 lecture notes on there. Um, Lecture notes from 29 distinct lectures. So you can have a look at that and see what's going to happen. But what I'm going to do is I'm going to post these lecture notes after class, after they've been corrected, and you'll see so you'll see exactly what I present in class. This will be available to you as PDF files. Um, you can take notes if you want to, although what I suggest you do is usually just take margin notes. That's the easiest. If I'm really on the ball, then I will have submitted these class notes, lecture notes before class starts, and so you'll be able to actually make margin notes on the lecture notes that I'm showing you here. Also, although sometimes that's not a good idea because you can see that I can because I'm using Notability, I can easily make corrections in real time to these. So you might want to wait until the corrected notes appear on Canvas. Otherwise, you'll get these and you don't have to take meticulous notes because they will be available to you. All right, so what are finite element methods? Well, first of all, I want you to get a picture in your mind of a set in R2 on which we're going to be doing a lot of work. So it doesn't have to be a particular set. We could use a square or a circle. I'm going to use just this arbitrary blob set, which I'm going to call omega. Omega is an open bounded set in R2, open comma bounded set in R2. It has an outward pointing unit normal on its boundary, which we're going to label as n with this little hat above it. That means it's a unit vector. Usually things with hats are unit vectors. The boundary, my notation for the boundary is always partial omega, but I'm going to also call the boundary gamma. So here's the statement of the model problem on this particular set. And by the way, we're going to assume what we need about the boundary of the set later on. You may know from your PDE course that it's important to know how smooth the boundary is to know how smooth a solution you could expect to have. We're not going to really worry about that quite yet. But that's coming, and it could be Lipschitz continuous if you know what I'm saying. It could be smooth, it could be C2. Don't worry about it so much right now. So our model problem is we want to find a function u that lives in this set. So this is fairly standard mathematical writing. We're actually looking for a function u, which is a function which takes numbers from the closed set. By the way, omega is open. If I put a bar over it, that means it's the closure of omega, and that becomes a closed set. So we're looking for this function u, which takes points in omega bar and assigns them a real value, right? So this is what we call a real valued function over a two-dimensional set. But I'm being a little bit more specific than that. I'm saying I want to find a set u, or a function u, which is twice continuously differentiable on the open set omega, and only continuous. This is my notation for the intersection, or and. So we need a function which is both C2 over the open set omega and C0 over the closed set omega bar. And sometimes I'll add the additional C0 over this just to make sure we're clear. C0 just means continuous, such that that function satisfies minus the Laplacian of u. If you've never seen this notation, Laplacian of u, that just means the divergence of nabla of u. So if I take nabla, that gives me the gradient of u. That's a vector derivative. And if I take the divergence of a gradient, that gives me back to a scalar. So the Laplacian is the divergence of the gradient of u. Okay? And that should be equal to a known function f, where where f is a C0 function over the open set omega. And by the way, let me know if you see any errors or, in the lecture notes as we're going along. So it has to satisfy this equation pointwise. Let's make sure it makes sense. Well, if I take two derivatives of a C2 function, I should necessarily get a C0 function, right? So that makes sense. So in this sense, I'm taking two derivatives of u, so the thing that I have in the end, this thing, the Laplacian of u, should at best be only C0. Okay, well, it could be smoother than that, but how can I say it? I'm only guaranteed that it's going to be C0. So that's why I'm choosing to look for that to be equal to a function f, which is well, it's at least C0. Okay, that doesn't look like a 0. Let's make it more clearly a 0. Okay, there we go, C0. And what else do I need? I also want to ask that u is equal to 0 on the boundary. And so rather than saying equal to 0 at all points in the boundary, I'm going to say it's equivalent to the 0 function as long as I'm on or residing on the boundary. So it should be the 0 function on this set partial omega, which I'm calling gamma. Okay, so that's a big if, right? Does such a function like this exist? Is it unique? It's not hard to prove that it's unique, but it is hard, at least in this context, to show that it exists. And we're going to come back to that once we talk about a particular, what are called Sobolev spaces. Some of you have seen Sobolev spaces before and some of you have not. And so I'm going to make our discussion of these things called Sobolev spaces, which are a particular type of function space. I'm going to make those fairly self-contained so that when we go over it, you won't need any external references. This problem, I call it a problem because it's an equation coupled with boundary conditions, and therefore it's not a simple equation. It's more than that. It's called a problem. And one question that I've already mentioned is, well, is that problem even well posed? We haven't answered that yet. It turns out this problem will be well posed generally, or in many cases, I should say. And it's called Poisson's problem. Poisson's problem. Now, if f is equal to 0, it's called Laplace's equation. This is called Poisson's equation. If f is equal to 0, then it's called Laplace's equation. And of course, if I pair it with this boundary condition, it turns out that the solution is only the trivial one for Laplace's equation. But you can get more interesting things if you use non-zero boundary conditions. But in any case, we're going to be general about this and talk about Poisson's problem and Poisson's equation. All right, so to analyze this in our finite element setting, we need an identity called Green's first identity. And I think I've gotten this right about my assumptions, but you can correct me if you see any mistakes here. So let's let V and W be functions from this open set. Actually, I think let's make it the closure. It doesn't really matter. I can easily extend it to the closure if I need to, but let's just add that. So W or V and W are functions that take every point in this closed set omega bar and assign a real number to them. So that's how we're thinking about these as two-dimensional scalar functions over two-dimensional domains. And we're going to assume about V that it's a C1 function over the open set omega and a C0 function over the closed set omega bar. W has slightly more regularity in both respects. It's a C2 function over the open set omega and a C1 function over omega bar. Then you've probably seen this result before. It says that, and it's kind of like an integration by parts. It's higher dimensional integration by parts, if you'd like. What I can do is, what I want to do, I should say, is I want to take this derivative, which is residing on the v, and I want to throw it over to this w. Okay, well, there's already a derivative on w. It's the gradient of w. So this is gradient v dot gradient w, and I'm dotting the two together. Okay, I'm dotting the two together to give me a scalar, then I'm integrating that over two-dimensional space. Well, over this two-dimensional set omega to be precise. I'm going to take the derivative off the v and I'm going to load it onto that. And of course, you know by integration by parts that that changes the sign of this integral from plus to minus. And there's the derivative now landing on w, and there's no derivative on v. But I also get a boundary term, and this is analogous to the boundary term that you have in the one-dimensional integration by parts. And by the way you remember this is just write out the one-dimensional integration by parts, and you sort of copy the structure. The only difference here is that this integral is now taken over the boundary set gamma, okay, or partial omega, if you like. Now, this is still a derivative. It's a special kind of derivative. Remember, we lift off the derivative of v, but we don't attach it here. It's going to come fully there, but this one still retains its first order status. But this is a special derivative that we call the normal derivative. And you've probably seen this before, and you've probably seen this notation. dw dn means you take that outward pointing unit normal, which is a function of the position on x, or the position on the boundary. If I change to another location on the boundary, then my normal might change to that, and so you can see how the normal derivative changes as I move around the boundary. This ds is my boundary element. Okay, so this is in 2D, this is going to give me a little line segment on the boundary. And this, of course, is my normal derivative. It means the normal dotted with the gradient of w. Okay, you've probably all seen this. This is a kind of directional derivative. All right, so that's our Green's first identity, this 1.2. And so let's massage this original problem here in such a way that we can use Green's first identity. Well, how can we do that? So let's take Poisson's equation and we'll multiply, I forgot to say, multiply by v and integrate. So multiply Poisson's equation by v and integrate, and what do you get? In fact, we're going to integrate over omega to be perfectly specific. So multiply by that v, integrate over omega. The minus sign comes out. Well, all I have to do then is to utilize this formula here, so I suppose, is throw that term over to the other side. This one already has a minus sign on it. Right? So my boundary term now has a minus sign, and the integration of the two gradients has a plus sign. So applying Green's first identity, I immediately get this. So multiply by v, integrate by parts. Green's first identity is just integration by parts in higher dimensions. And then apply the condition from the Poisson equation. And so sometimes I'll use this notation 1.1. That means the equation here. And so this is the first equation of one. This is 1.1 is comprised of exactly two equations. So this would be 1.1.1 and this would be 1.1.2. So we'll use that notation. So because we're using that fact there, then this, remember, well, let's see, do I have... let's see, I think I forgot to write something, right? Let's see. Oh no, we're okay. Why is this so? It's so because this is going to be equal to that, right? By virtue of the fact that this with the minus sign is actually equal to f pointwise. I got confused there for a second, but because this is pointwise equal to f, this is true. Okay. Well, now what I'm going to do is I can use this identity and this fact to say that this equals that. And that's what I'm wanting to do. So next we're going to suppose, well, by the way, I don't want to miss something here. I may have, you might think I cheated a little bit here because, well, why have I cheated? Because I said that the model problem is to find u in this set C2 intersects C0 omega bar, right? And that's the minimal things I need to have this problem defined in a sort of classical sense. I need the C0 because I need this to have point values on the boundary. Okay. So that's the easiest way most convenient way I know to do that. Okay. So this allows me to make sense of that part. And this, of course, is to make sense of this equation point-wise. Now, but notice that I've cheated a little bit because I bumped up the smoothness. This is called regularity. I bumped up the regularity of u a little bit by asking that it be C1 on the boundary. Okay, C1 on the boundary, which is a little bit more than I required before I just had that as C0. Why do I need it to be a C1 on the boundary? Well, I want this term to make sense. Du dn, and it will make sense as long as it's a C1 function on the boundary. Okay? Or up to and including the boundary, I should say. Okay, so that's where or that's the reason I've added the extra regularity. Now, what do I need for this thing we're calling v? The thing v here is what is called a test function. V is called a test function, or what is it also called? Maybe it's called a trial function, but at least it's definitely called a test function in many corners. So what do we need for this test function? Well, we need it to be C1. Why do we need it to be C1? Because I want it to be able to accept a gradient, okay? And so if I'm to take the gradient of V, to make it understandable, let's just assume that it's C1 in the open set omega. And why do I need it to be C0 up to and including the boundary? Because I want this term to make sense. Okay, and as long as these two things are continuous on the boundary, then this boundary integral is going to make sense. No problem. All right, now we get to the crux of the matter. We're going to assume or suppose that V is equal to 0 on the boundary. That's exactly the same as what we normally assume about the solution U. Okay, but notice that we're not really taking any, we're not concerning ourselves with what the solution U is doing on the boundary. It doesn't matter to us at this point, at least. So if V is equal to 0 on the boundary, like U, its sort of counterpart, then this term is going to vanish. And then of course, we have the equation of these two terms. I probably should have put this guy up here just to have it make a little more sense. But in any case, these two things are equal. And so that means that I have equality here. Okay, this term having vanished. Right, so what do we have now? Well, we started from the strong solution, although we did bump up the regularity, we made the true solution a little bit smoother, and that might or might not be fair to do. I'm going to show you later on that it doesn't matter. We can always do this sort of bump up. And I'm going to use what's called a density argument to show you that in a while. But in any case, we don't need that sort of sophistication yet. But what we know is that this equation is now an equation of numbers. It's just real number equals a real number, right? This this very simple equation of real numbers, it has to hold for all v in this set. C1 omega intersects C0 omega bar. But it has to have something additional, right? And the addition is we want v to be equal to 0 on the boundary. So let's take that and define a space. Let's define a space. And then I'll try to explain what's going on. So the space that we want is going to be, first of all, the space for our trial solution or our test function. Okay. So v is what we're going to call this space. It should be the set of all functions v in C1 intersects C0 omega bar, such that v is equal to 0 on the boundary. Well, can we do this? Does it make sense? Well, it has point values on the boundary. No problem there. So we can assign its values to be whatever we want. So is it a space, a linear space in the usual sense? In other words, can I add two functions from that space together and be guaranteed that we're going to be back in the space? So this is, I don't like that. Let's see here. Or vector space. Linear space or vector space. Bona fide means a good and true. All right. Right? Because I can take any functions, and if I add them together, I'm going to get another function from the same class. And if the functions are both 0 on the boundary, and then I look at what is if the sum of the two functions is also 0 on the boundary, then clearly it will be. And if I take any scalar multiples of these functions, then the scalar multiple will also be in the space, or will also be in the set. So it's a linear vector space. Okay, so now let's define a couple more objects. Okay, so the first one is going to be a type of bilinear form. So, and let's be very careful and make sure everything makes sense. So here we go. So the bilinear form that I'm going to define is this thing I'm going to call A, the A form. Okay, it's going to be a function of two functions. Okay, a function of two functions, which should remind you of something that we call an inner product. Okay, and to compute this, we're going to integrate those two functions. And in fact, not the functions themselves, but their gradients. So take the gradient of u and take the gradient of v, dot that together. That gives you a scalar function, and then integrate that, and that gives you a number. So this passes the first test of something called an inner product, right? So a real inner product should be if I put two functions or vectors in, then I do something with this, operate on it in the way that the inner product dictates, and out comes a number, right? So that makes sense. Right, so what else? Oh, by the way, before I forget, let me put this on do not disturb so we don't have any disturbances. Okay. Right, so that all seems to make sense. And by the way, notice that u and v are both from the space V. And the space V demands that the functions are at least C1 in the open set omega, and that's enough for this to make sense. Now, we don't know if, we don't quite know if this integral will be bounded, right? We don't know if it'll be finite if we just have this. So that's an open question. If we said it was C1 over the closure, then we'd be fine. We would be fine. But we'll get to more of these technical questions a little bit later. what else are we going to define? So we defined a space, we've defined a bilinear form, and now we're going to define a functional. So functional is a function of a function of a or vectors or something like that. So it should turn, so we're going to assume that f is given, but this v is going to be free. So if I put it in a function v and I integrate it against f over omega, then I should get a number. Each time I do that with any function that's kind of nice or nice enough, then I always get a number. Well, f itself, we said, was going to be a C0 function, right? And so we are going to integrate that against v. So I don't know if this is going to be finite for every v either, because f could be bad near the boundary. And of course, I could fix this up to make f not so bad near the boundary. Right. So now we have all the tools that we need to define a weak formulation of the model problem. So here's the weak formulation of the model problem. We're looking for a u in the space V such that, so remember V is this setup here. It only has one continuous derivative by assumption. Whereas remember the quote unquote true solution for the original model problem had two derivatives, but we're only demanding now that it has one for this so-called weak formulation. Find u with one derivative such that AUV is equal to f of v for all v in capital V. I'm missing a period there. This is what we call the weak formulation of the Poisson problem. Why is it called a weak formulation? Well, it turns out if u solves the original problem and has a lot of smoothness, then it also satisfies the weak problem, which doesn't require as much smoothness, because for the test functions and for the solution space itself, our demands are only that v has one derivative in the interior, one continuous derivative at this point. All right, so here's the mathematical statement. If u solves the original model problem and it has this extra regularity attached to it, it's C2 in the interior and C1 up to and including the boundary, then u also solves problem 1.6, which is what we call the weak formulation problem, right? It will have more derivatives than we need for this problem, but at least we know it has to be a solution according to this proposition, if it's true. Well, we already know that this proposition is true because we developed the weak formulation from the model problem, the so-called strong formulation. You just apply Green's identity in the way that we did before. Of course, we had to assume a little bit more smoothness for you to apply that Green's identity properly, although I will show you later that that's not needed, and we can get away without that. But the proof is already done for us because it was a proof. It was kind of a constructed thing to begin with. Well, naturally, you might wonder, is the converse true? Well, maybe it could be true, but we don't know for sure, and we don't have enough tools yet to prove that, because one of the stumbling blocks is if we assume that u is a solution to this, then it only is a C1 function. However, in the interior, that is. However, we could say, well, suppose that it's a solution to this, but it has extra regularity, extra smoothness. Could I then show that it's a solution to the standard model problem? For example, if I assume that u has this much smoothness. And the answer to that question is yes, you can do that, and it requires just a couple of steps, although we don't go through them here. So the converse can be answered in the affirmative if my weak solution has enough smoothness, enough derivatives available to it. Although we don't, I haven't yet given you enough machinery to show you that that could or even maybe could not be the case. So this requires what's called regularity theory, which we'll cover at some point. Next, I want to give another formulation of this problem called a variational formulation, which is more like the weak formulation than it is like that original strong formulation. So here it goes. It uses the same ingredients, but mix up in different ratios, I guess, than the weak formulation. And it goes like this. Let's look for a function u and v. Remember, this is my weakened derivative space, such that u is the argument that minimizes this function g. Okay, now this is already kind of a blasphemy to mathematicians because I'm saying that there is an argument that minimizes g without proving fully that we should expect one. Or I'm saying it's equal to the one and only argument that minimizes g without proving that this thing is uniquely minimizable, or right, that has a unique minimizer. But in any case, let's proceed under these sort of assumptions, and with the knowledge that we actually can prove that a unique minimizer exists. Now, the function that we're going to minimize is this function I'm calling g, and g is equal to 1/2 avv minus f of v. So it's only a function of a single variable, not really two variables, right? Before the bilinear form, a is technically a function of two variables, but I'm putting in both locations v and v. Okay. So what I want to show is that u solves this new problem 1.7 if and only if it solves the weak formulation 1.6. And this problem is going to require a leap of faith that we'll come back and prove later, and I'll talk about that once we get to that point. Okay, so let's go this direction first. This direction means we're going to assume that it solves 1.6 and try to show that it solves 1.7. So suppose that u solves 1.6. That means that it solves the weak formulation. And of course, it's in, I should say u is in v, but that's kind of, I hope that that's understood. I hope that that's understood. I think I set it up here. Okay, so it's in v and it solves 1.6. Let's let w be an arbitrary function in v. I'm going to call these functions, but later on I might just call them points because well, it's an element of a set, and a lot of times we say an element of a set is just a point, okay? But in this case, you should understand that this point is really a function, right? But we're going to let that be arbitrary, and I'm going to examine g u plus w. U is that special function which we said solves 1.6, and w is anything else arbitrary, okay? Arbitrarily chosen. So if I expand this g using the definition and using the fact that this is truly a bilinear form, okay? And bilinear means it's linear in its first argument and it's linear in its second. And by the way, it's also symmetric, right? It's a symmetric bilinear form. And I'm going to use that fact as I go through. So the fact that it's a symmetric bilinear form means that when I expand this, I get 1/2 AUU plus AUW. The symmetry comes in adding 1/2 AUW plus 1/2 AWU plus 1/2 AWW minus F of U minus F of W. Okay, so that's just what I get when I use my definition here. I'm using the bilinearity of A and the linearity of F. Okay, and now I'm going to group some terms together. Let's group this term with that term, put them side by side. And otherwise, we're not going to change anything. We are going to also pull this guy together and that gives us G of U, right? So it looks like G of U plus W is just back to G of U plus something which turns out to be 0, right? Something which turns out to be 0. And why is it 0? It's 0 because of 1.6, because U is a weak solution. So that's 0 plus 1/2 AWW. So G of U plus W is equal to G of U plus 1/2 AWW. Well, suppose that w is not equal 0. If that's the case, then we can show that, and this requires a little bit of showing, but maybe maybe it's clear to you. If w is not identically the 0 function in V, then it must be that AWW is strictly greater than 0. Okay? So if you look back at how A is defined, that might be clear to you. As long as I put in two arguments here, W and W, WW, then this is a gradient of W squared. And the only way that that could be equal to 0 when I integrate is if the function was identically 0, which it would be allowed to be in this function space. But we're going to disallow it by definitely assuming it's not 0. All right, so this we're going to come back to, but I hope that it's I hope that this is kind of clear using these continuous function spaces. In fact, we can show that AWW is equal to 0 if and only if W is equal to 0 in that space V. It's a fairly nice space. It's nice in some senses. It's not nice in some other senses. Well, that means, and I've got it written wrong here. This should be, it's a typo. That should be G. So it's clear that, well, this is always greater than or equal to 0, but it's strictly greater than 0 as long as W is not equal to 0, right? So we can clearly show that G of U plus W is greater than or equal to G of U for all W, and the equality is strict if W is equal to, let's see, yeah, is not equal to 0. As long as we're not equal to 0, actually I can say if and only if, right? If and only if W is not equal to 0. Well, if U is a function that satisfies this inequality with that property that it's strict as long as W is not equal to 0, well, that means that that U is a unique minimizer of G. It has to be a unique minimizer of G. It's always less than anything that you obtain by examining U plus W, right? And this can be arbitrary because we're in a linear space. So this is essentially like saying let Z be arbitrarily given, then G of Z is greater than, strictly greater than G of U for any Z other than U, right? So that's exactly what we mean by a strict minimizer or a unique minimizer. So that direction is done. Now, of course, we still haven't shown that we have enough information to say that this has a solution or not, right? We're just supposing that it has a solution, okay? Now, we're going to go the opposite direction, and we're going to suppose that U solves 1.7. We don't know yet if we have enough information to say that it always has a unique solution. And we're going to suppose that W is in V, and W is not equal to 0, and S is a real number. And then we're going to consider this function G of S. G of S is big G of U plus SW. Okay. Well, I can expand this the way I did before. And it's not too difficult to see that what I get in collecting terms is I get G of U plus a quadratic term in S squared over 2 AWW. And I also get this intermediate term here, which is just going to be S, A of UW. I'm using the symmetry and bilinearity of A and the linearity of F, and I'm gathering these two terms together. Right. Okay, so I haven't done all the details, but I hope that you believe that they're true because you can use the linearity and go through this. And some of you have seen calculations like this before. Now, for fixed U and W, this is simply a quadratic polynomial in S. You agree? just a quadratic polynomial in S. And now we've assumed a priori that U solves 1.7, which means is a global minimizer, right? So let's look at this function G. What is it doing? It must be doing something like this. It must be a quadratic of that form. Well, it opens upward according to that term. So that shape, right? It's definitely that way rather than that way. And of course, S is along this direction, right? And now I know that if I set S equal to 0, it just gives me G of U, and so that should be the minimizer. Well, what can we say about this function further? Well, it's a quadratic polynomial, we said that, in S. It's convex since this coefficient here is strictly greater than 0, and that was because we're assuming W is not equal to 0. S can be anything at this point, we don't care. So it must be true that G of S has a global unique minimum at S equals 0. Why at S equals 0? Well, because this is just going to be kind of like a section cut out of this I guess you can view this as like a paraboloid, and we're cutting a section out of that. But notice that the section is going right through U, because W is fixed and U is my minimizer, and S is just some parameter. So the way I should view it is like this. I'm going to view it in kind of a two-dimensional space setting. So here's my U, and here's W is anything. Okay, so W is anything I choose, right? And so U plus SW might be out there for some given S, for some positive S. All right, so, but otherwise, let's see if I can make a dashed line here. Can I? Yeah. So it's cutting through U like that. Now so that's what I mean by a section of this paraboloid through U. So as S changes, I'm moving to different locations on this line, right? And as I'm doing so, I'm evaluating G. So this function, if I were to be able to plot this, function would look something like that on that line. I hope you get the idea. Right? So it has a minimum at U because U is the global minimizer of this function G to begin with. So what do I know then? Well, this is a smooth function of S. In fact, it's the nicest kind of smooth function of S. It's a polynomial. So that means if it has a global minimizer at S equals 0, which we know it must, because U is the global minimizer of G, then it must be true that if we take the derivative of G with respect to S and set S equal to 0, we must get 0. That's just the derivative test, right? It's just a derivative test from calculus. Okay, but this, it's easy to take the derivative of this function, G. It's a simple quadratic. So take the derivative, set S equal to 0, and what happens is, well, this term goes away when I take the derivative. Is simply a constant. And this term is going to go away too, because I'm going to get S over 2, but I'm going to set S equal to 0. This S goes away when I take the derivative, so the only thing that's left is that. So if I take the derivative and set S equal to 0, I get this. But remember I said it must be true that when I evaluate this derivative at S equals 0, I get 0 by the derivative test. So if this is equal to 0, I must have that. But now think about W. W is anything in V that was not equal to 0. And so this holds for all W not equal to 0. And otherwise, W is arbitrary. So I've shown that this is true for all W, but as long as W doesn't equal to 0. But what about W equals 0? Well, it's trivial to show that this also holds for that case. If W is the 0 function, then of course this is going to be, these two things are going to be equal. There's nothing really there to do. So that takes care of the W equals 0 case as well. So I've shown that the variational formulation and the weak formulation are really one and the same. This isn't always the case, but there are a couple of things that I used in here, which are kind of hidden nuggets. One of the hidden nuggets was the fact that we used, without saying much about it, that A is a symmetric bilinear form. If A was not a symmetric bilinear form, then when we calculate this expansion, we wouldn't get this term here. Okay, you can see what you would get in that case by doing the example, but suffice it to say, we would not have such a simple form if A was not symmetric. So we did use that. What else did we use? We used the bilinearity of A. So that means probably if I'm using or working with nonlinear PDE, my arguments would break down a little bit. I need linearity somehow. And we'll discuss this a little bit later too. For example, because we're going to be interested in talking about functions that look like this, minus Laplacian of u plus u cubed equals f. Well, that problem is nonlinear, and I can't write a bilinear form for something which is nonlinear. So there'll be trouble there. Okay, what else did we use? We used the linearity of f. That's not such a big deal. So our original problem started out as linear, but what are we going to do with nonlinear stuff? Well, that's a good question. Well, we're going to have a lot of problems to deal with. One of them is that the weak formulation that we provided isn't weak enough for our purposes because it's not nice enough to give us the peace of mind that we always have a solution to our weak form or our variational formulation. So we're going to have to do something different, and we need to use what's called some Sobolev spaces to make some progress. The Sobolev space that we'll end up using for this model problem is what we call, in most of the people use the same notation, H01. So this notation means the Hilbertian Sobolev space H1 with the restriction that functions on the boundary are equal to 0, if this can even be possible, which is this space, V set of all L2 functions, such that these things, these objects here, which are called weak derivatives, are also in L2, and V is equal to 0 on the boundary. Now, if V was only an L2 function, you guys probably know from at least those who have taken this course before in measure theory, know that if it's only an L2 function, then I could never guarantee its point values on the boundary. Okay, that's not possible. But because it has these weak derivatives also being in L2, it turns out that I can, in some sense, tell you what the boundary values are, at least with what we call up to measure 0, or so up to a change of a function on a set of measure 0. Now, we're not going to worry about this point too much yet. We'll get back to that a little bit later. And instead, we're going to push on with talking about, at least in this abstract setting that we're going to use, first of all, what we mean by finite element methods. Well, really, to be truthful, we're going to talk about something called Galerkin methods first, and these work out to generalize what are called finite element methods. All right, so let's let VH be a finite dimensional subspace of V with this basis. Well, if I'm a subspace of finite dimensions, then how can I be guaranteed that it's going to have a finite basis? Well, that's kind of a tautology, really. If it's finite dimensional, then it has a basis of finite number of elements, and its dimension is precisely the number of elements in any one of the bases. And any basis has the same number of elements, but the basis is otherwise not necessarily unique. So this basis, all that we're going to require of it at the moment is that it has m elements, or a finite number of elements, and each element has to be originally in the space V. Okay, so that makes sense, because if it's a subspace, then each one of these is in VH, which is a subspace of V, meaning that each one of those functions has to be in the original parent space V. Of course, our dimension is exactly m because there's exactly m elements in our basis. There's no ambiguity there. Once I tell you it's finite dimensions, then it has some dimension. Its basis has exactly that number of basis elements. But this is all we need to define what's called the Galerkin method. You might thought that we need V to be a Hilbert space. We don't. We don't need anything more or less than this very generic framework. And then we're going to get into Hilbert space theory a little bit later. Find the Galerkin method is to find UH and VH, and I use VH to represent the fact that I have a finite dimensional subspace. You might say to yourself, how are H and M related? And there's no clear way, but the way I usually think about it in my mind is, in the back of my mind, I'm thinking that H is equal to 1 over M. It's not. It's not equal to necessarily 1 over M. But that's how I think about it. In one dimensions, and if I have a uniform mesh, then that's the case, okay? So that's how H and M are related to each other, okay? But they're not that carefully related. I'll show you why later on. So the Galerkin formulation is to find a function in that finite dimensional space such that A of UH against V is equal to F of V for all V, not in the original parent space V, but in VH. It's restricted to VH. That's it. That's the finite dimensional, that's the basis of the finite element method. You learned that in the first day of this class. It's just this, it's asking us to find a function from this finite dimensional subspace of V such that this holds for all test functions in VH. Okay, the test functions are now from the subspace. The Ritz-Galerkin method is slightly different. The Galerkin method uses the weak formulation. The Ritz-Galerkin method uses the variational formulation. And the Ritz-Galerkin method is find UH and VH such that UH is the argmin of GV taken over all functions V in the subspace VH. Now, I can show that these two things are equal to each other. That this, well, I can show that if UH is a solution to this, then it's a solution to this problem, and vice versa. So that means the solution sets are equivalent. But what I can't show you yet is I need a little bit more machinery to show you that I'm guaranteed to have a solution for this. Okay, well, this one turns out I don't even have to know that V is a Hilbert space to show you that this has a solution. And I'll show you what I mean momentarily. Well, actually, it's going to wait till the next lecture. But that just uses some properties of symmetric positive definite matrices. And the same with this. I don't need to know that V is a Hilbert space. I only need to know that the space in which I'm looking for solutions is finite dimensional in both cases. And then I'm going to encounter this thing called the stiffness matrix. And the stiffness matrix we're going to show by virtue of the fact that A is a symmetric bilinear form that that has another nice property associated to it, is positive definite. And I can show that even if I don't have knowledge about V being a Hilbert space. We'll talk about that in a minute. Well, as I said, later, next class. Okay, so recall our definitions, right? These are the big three that we made so far, I guess excluding V, what the definition of V was, but that's what we're going to use in our working definitions. Let me remind you that we had this bilinear form lying around. And from that, we can create a norm, okay, or something I'm going to call a norm, but then I'm going to show is a norm in a minute. Okay, so that norm is called the energy norm. For all V in capital V, define the energy norm this way. You take that bilinear form, you're going to throw into that both locations the same function, V. This we can show is going to be an integral with a positive or at least a non-negative integrand. And so I'm taking over, integrating over a set of measure non-zero positive measure, and I take the integral, I'm going to get something which is greater than or equal to zero. And only equal to zero if V is identically equal to zero in the space. Okay, so it's going to be something that we can show as a norm, an actual bona fide norm. But right now we're just going to give it the moniker energy norm as if we knew that that was the case. Well, to prove this, the easiest way to go, I think, is to show that A is an inner product on this space, and this is an induced norm. Now, some of you have studied Hilbert spaces, you've studied inner product spaces, and you've studied normed linear spaces. And I'm not gonna necessarily assume that you've seen that stuff, and we'll go through these things fairly carefully once we define what we mean by a Hilbert space, and that will come a lecture or two from now. So don't worry too much about this yet. But the only difficulty here with this problem is that we want to prove it, as a part of A being an inner product, that it is that it has this positive definiteness property, which means that we want to show that the only way that AUU could be equal to zero, this is the only difficult point, is that U is identically equal to zero in the space. Okay, remember the space is kind of nice because it's C1 functions, which are C0 up to and including the boundary. So we're just going to assume that this is true for now, and we'll come back and talk more about this later. But that's the only difficult point that we need so far. If you have any arbitrary inner product on a linear space W, let's assume that it looks like that, and we're assuming that the vector space of the linear space W is a real vector space, and the norm associated with that inner product, what we call the induced norm, which is defined like this, right? And it has a norm. If it's an inner product, then you can always create the induced norm, which has this structure. Then we have this inequality holding, which is called the Cauchy-Schwarz inequality. Okay, for all U and V and W, then the absolute value of the inner product of U against V is less than the norm of U times the norm of V, with equality if and only if U and V are linearly dependent. So again, you don't need this to be a Hilbert space to prove this. You just need to have an inner product. Well, first of all, if either U is equal to 0 or V is equal to 0, 1.11 is trivial, right? Because I'm going to get 0 on that side by linearity of the inner product, and I'm going to get 0 on this side because this will be 0 or that'll be 0. So let's assume that that's not the case, that neither of these two are equal to 0. And let's define this function P of t. You might have seen this proof before. It's a fairly standard one for the Cauchy-Schwarz inequality. P of t is equal to tu, it's the inner product of tu plus v against the same thing, tu plus v. And now I can expand. Remember, all bilinear forms, or all inner products are bilinear forms that are symmetric. And so because of the symmetry, I get a 2 here, T UV. If it wasn't symmetric, then I wouldn't have a simple term in the middle. I wouldn't be doing this calculation in the first place, I suppose. Okay, now we're assuming that u is not equal to 0 and v is not equal to 0. So what do we know about this function? Okay, well, if u is not equal to 0 and v is not equal to 0, then p of t is strictly greater than 0 unless the sum of these two is equal to 0. That's the only way, because this could be 0 and that and therefore that could also be 0. In that case, p would be equal to 0. All right, I should say p of t is greater than equal 0 for all t. Unless for some t, tu plus v is equal to 0. That's the only way we could get a kink there. Well, let's assume that this isn't true. Okay, if that's not the case, then this is strictly greater than 0 as we supposed, and therefore this is just another quadratic equation. What do we know about this quadratic equation? For all t, it sits strictly above the real line. Therefore, it has no real roots, right? It only has complex roots. It's a quadratic equation with no real roots because it's always sitting above the real line. Well, functions such as this have the property that it's discriminant, right? The discriminant, which is going to be b squared minus 4ac, right? Well, this is b squared here, 2 times that, well, squared, that's b. And a is equal to u squared, and c is equal to v squared, so that's where all this comes from, right? 4ac, we can pull a common factor of 4 out front. This discriminant has to be strictly less than 0 because when I take the square roots, I'm going to get complex numbers. Well, that says that since 4 is known to be positive, the only possibility is that this guy is less than or equal to 0. Now, I can, there's an easy argument to show, and I didn't do it here, but it's an easy argument to show that if I get that, this thing being less than or equal to 0, I can show the same with the absolute value, with the negative. And all I have to do is switch one of the u's or v's to its negative value. So I'll leave that up to you. You might be saying, you didn't prove it because there's no absolute value there. Well, that's a minor detail. Now, now we've got one more thing to come clean up, and that is if that is equal to 0. If that is equal to 0 for some t, then we know that at that t star, then my polynomial is equal to 0, and otherwise it's greater than or equal to 0. But that means the discriminant is exactly 0 because p has a double root at t equals t star. And if t has a double root at t equals t star, well, that shows again that this is actually equal to that the discriminant can only be 0 if this thing in the middle or in parentheses is equal to 0. Okay, so that's the Cauchy-Schwarz inequality. Now, I don't have time to go into the next thing, so this will all get moved to the second lecture. We'll start talking in the second lecture about the fundamental Galerkin orthogonality, and the next thing on the list was Say's lemma. So, like I said, if I were to post these things online to begin with, I'd end up revising them anyway. So the revised set of notes will stop here, and all this stuff will go on lecture 2 notes. And the way I'll do my numbering is lecture 1 will be numbered with 1 point something, and lecture 2 is going to start off with this equation. It's going to be back to 2.1 and then 2.2 and so on. So things will get numbered a little bit differently. Okay, you can turn your cameras back on. We're done with the first lecture. Any questions? Okay, so these videos always go directly to the cloud. So if you're wondering where they'll be located, they're always going to be on Zoom, unedited completely. So if you missed any announcements, that's where you go. All right, if you missed the class. The ones I put on YouTube, I'll create a channel. Well, I have a channel, but I'll create a new playlist for this one, will be Finite Element. And some people like to watch those because they're edited, and of course, when you're on YouTube, you can speed them up to 1.2 1.2 or 1.5, right? And speed through a lecture. So that would be where to go if you wanted to watch the edited videos at a faster pace. But I will warn you that if you watch only the videos on YouTube, you might miss an announcement because I don't necessarily put all the announcements in there. I cut certain parts out, and I cut students' faces and identifying information out. So just that word of warning or message of for your information, I guess. Any questions before we go? Okay, if not, next Thursday will also be online only. Remember, I said Tuesday and Thursday online only. And then if we decide to meet in person to fulfill our hybrid mission, then that would be Tuesday. And I guess the way we're going to do it is, of course, the people that aren't here clearly want to do online only because they can't attend synchronously. So what we'll do is if you have a compelling reason to want to meet in person, why don't you just send me an email and we'll do it that way. And that will tell me whether anybody wants. Now, like I said, if it's only 2 people that want to show up for the lecture, then maybe we'll just do it online. Okay. All right. So have a nice day, and I'll see you guys on Thursday.